and that's okay. That's correct, right? I mean, there's no wrong answer here. That's one of the correct options. However, if you think about it, like in the case of, let's say, this is just one study, one site that I simulated. But let's say that you actually have a data set where you have this response for many sites in many years, and you're trying to find an overall response of seeding rate to yield in Kansas, right? I would say it's more unlikely, it's less possible that this generalized response over many sites and many years to be linear plateau, just because we know that biologically, especially with seeding rate, it doesn't take that much more seeding rate to start decreasing yield. So the more biological sound model, if you think about it, is actually the quadratic. So if we were to make a prediction for someone, I would personally choose the quadratic, because that would be more representative of reality, even though the linear plateau had the best fits. And that's okay for this single site, single year, that the linear plateau had the best fits, and we use that to find the optimum. That's okay. But if we're trying to generalize things, then I think we have to think more about the biology behind it, because it is going to have a larger implication, right? Okay, so I personally, if I were to use one of these models for predicting an output for somebody, I would use the quadratic because of what I just said. So now let's suppose that we did indeed have enough data coming from multiple sites, multiple years, and we did the quadratic fit, and we came up with this equation that is like used for Kansas, because all studies are all across Kansas, and we analyze it properly, and it's a good equation for predicting response of yield to seeding rate in Kansas. So we have this model. We trained this model with this complete data for the state of Kansas. And now a producer comes to you and says that she's considering changing her corn seeding rate from 70 to 90,000 seeds per hectare, and want to have some idea of what could be the potential effect that management change could have in her corn grain yield. So we have the data, we have the model. Let's give this producer a prediction. So you can come to the next chunk. So I gave you a little bit of code, but not the complete code. So you come here to the producer SR, we add the get sign, and then let's create again a data frame using the data frame function, where the column we want to create is the SR capital underscore KSAJ, the same that we've been using. And here, I'm not going to create a sequence of values. I'm just going to give two values, which are the ones that this producer is asking for. So that is the 70 and 90,000 seeds per hectare, right? So I just create this and I print this data set so you can see it. It's a very simple data set. It just has one column, two values, that's it, right? So now we can come down to the next part of this. So it's still the same chunk, but if you come here to the mutate, we have the predict function, where we're going to be using the quadratic model fit. So the reg quad underscore mod, and then comma, hit tab. We're going to say new data. This is an argument, new data equals producer SR, which is what we want to predict, comma, re.form equals NA. Just again, to ignore the random effector block here. So if we just run this and you print it, there we go. So we have those two seeding rates that we want to predict yield for, and then we have the predicted yield using the quadratic model for those seeding rates. Sweet, that's what we want. However, even though maybe a farmer is not as interested in error bars as we as scientists are, they maybe just want to know the average. This would be the answer. This is the average. But I want to show you again how we can calculate error bars around these two values. So again, we're going to use bootstrapping for that. You can just run, let's see here. I think I gave you, I think you have almost all. So you can run the predict fun too, and then you can run the producer boots. That's a nice name, I just realized. It's going to take a little while because this is the one doing the bootstrapping, which simulating 200 times. And then here on line 568, where we have the producer SR, I want you to add a pipe after that, hit enter, and then we're gonna say bind underscore cols. And inside the bind cols, we're gonna have the producer underscore boots object. So we're basically just adding this 2.5 and 97.5 column limits to the original producer SR object. And then you can just run. You're gonna be able to see now that we have then the seeding rates we are predicting for, the yields that were predicted for those seeding rates based on our model, quadratic model, and then the lower and upper confidence limits. Oh, this is actually UCL. This is not going to change your code. It's just I had a typo there. Upper confidence limit. Yeah. So I just did that. It's going to take just a little time to run, and then we can get back on track. So we're getting very close to the end. Maybe like next 5 minutes, we're done. Just so you guys know, we're not going to be super late. So just run that again, and then run this. You know what? Actually, when I changed what I changed, it made some funky stuff because it had similar columns already. For this to work, we actually have to rerun this entire chunk here. Sorry about that, but if you could just go up a chunk, you can just hit the play button and it's gonna just rerun that entire chunk. And then if you go to the chunk below it, you can again just hit the play button because it's gonna run the entire chunk. And then we should be gold. All right, there we go. So now is what we wanted to have. Okay, so now let's just make a quick plot. You already have all the code there. You can just run it, just so we see what is the difference. Oops. Sorry, so you're gonna have a typo there, as I just noticed now. So the Ymax, I said UPL, is actually UCL, just to let you know. And then you can just run it and it should work. So this is what we would basically tell this producer, that if they increase their seeding rate from 70 to 90 thousand seeds per hectare, this is the range of possible of 95th percent confidence interval that they would have a yield at 70 and at 90,000 seeds per hectare. And again, if you don't want to look at the plot, you just want a table, we can always come back to the table up here and give actual numbers to someone. And something I want to point out here is, hopefully you have already realized this, but 70 and 90,000 seeds per hectare were not part of our study. We did not have those levels. And this is one of the beauties of regression, right? Regression can help you to make any prediction in the interval of values that you evaluated. Anything in there is fair game. If you try to predict something outside of the range that you evaluated, that's iffy, right? People can do it. I mean, the model is not going to throw you an error. It's still going to do it, but maybe you shouldn't, because you don't know what happens outside that range, right? Because you didn't study it. But anyway, 70 and 90 were within the range. And even though they were not the actual levels that we studied, but we were still able to predict them because we did a regression. Okay, so I just had a few sentences I wanted to tell you here. So to kind of wrap up, right? What is the difference between using ANOVA and regression? ANOVA is really good to understanding your study that you have at your hands, like what you conducted, and you want to understand how different means of treatments are being affected, or how treatments are affecting the mean of your output. ANOVA is the way to go. That's the best way of learning that. You're going to have letter separation, you're going to have means, you're going to have letter separations, that if that's what you need and want. And regression, on the other hand, even though it's doing a very similar thing behind the scenes, but it's not really interested in means of certain levels. It's kind of looking at the entire picture and understand the entire behavior to come up with an equation a mathematical equation to describe that relationship. And then you can use that to find optimums and to predict as well, and possibly other things that I haven't thought of, but those are the two that at least I use the most. And another quick point here, so a take-home point related to finding optimum. As we saw, optimum is something that really depends on the study. So even if you have the same study over multiple years, you can have different responses. So just because you had a quadratic this year doesn't mean you're not going to have an intercept response next year or maybe another site. So we always have to run multiple possible models when we're trying to estimate the optimum, and then choose the model that best describes that data set, and then use that model to find the optimum. And also a point that we really want to reiterate here is that do not simply rely on p-values. ANOVAs can give you highly significant p-values and yet be completely wrong, as we saw in one of the examples. So always check the residuals, and I gave you some tools to do that here. So please use them in your research. That's gonna make your research more robust if you check your residuals. And so that's basically the take home I had. 3 sentences for final thoughts. I will share both of the complete scripts with you probably tomorrow. So if you missed something from yesterday, or maybe if you missed something from today, you're gonna have the complete scripts. I'm gonna send them to you. And when I do that, I'm gonna send you a survey for you to fill. And I really, really want to ask you to fill that survey. It's not going to take too long, but it's going to basically help me to get feedback from you, from what you learned, what you wished I had done differently, what you liked, so I can understand how the workshop went, and I can improve for future workshops as well. So I can get something out of this as far as getting your feedback from how just your overall thoughts on the workshop. So I will send that to you. Please fill out the survey as well. That's going to help me a lot. And I think that's everything I had. So let's see, 6:07. Guess we're not terribly late. If you guys have any questions, the floor is open. Feel free to unmute yourself. This is okay to unmute yourself. And if you want to type in the chat as well, that's okay if you don't want to be speaking up. And thanks for attending. Thanks for being part of it. Hopefully you got something useful out of this, and you got my contact if you need to reach me, and we'll be in touch.
So thanks, Leo. On behalf of the AGSA, I want to thank you for this great workshop. So hopefully it will help everyone that attended the workshop, and with data analysis. That usually is a terrible time, I would say. Depending on your research, of course.
Yeah, no problem. Thank you guys for inviting me again this year. It was fun. I mean, it's kind of different to do remotely. Last year, I could look in people's faces and at least have some hints if I was going way too overboard or way too fast. This year, without that feedback, the live feedback, was kind of interesting, but I think we made it work.
I think so. I think it was great.
Yeah, I like the codes are very neat. Yeah.
Thanks. Yeah, when I of course my personal codes are not as detailed, but then when I'm giving workshops, I try to think what's the easiest way to convey something and not just do something. So hopefully I was able to to do that successfully. All right, let's see. We have some comments here, but lots of people saying thanks. Thank you everybody for the messages. Thanks for attending. I'll stick around for, I don't know, maybe a few more minutes if anybody has any questions or thoughts. And if you want to email me any questions, any thoughts, you have my contact, feel free to do that as well. And so just hang around for a few more minutes if anyone wants to ask something.
Okay, we'll just talk